talk about my work on the quantum phase transition of random disorder system using deep learning. So in the last few years, I started this work 3 years ago, and after that, there seems to be a booming of machine learning, application of machine learning to condensed matter physics. And what I'm going to talk about is just a part of the vast applications of machine learning to condensed matter physics. I will focus on this, in this talk, I will focus on the quantum phase transition in disordered system. So the outline of my talk is that it's to study the quantum phase transition of random system by analyzing the wave function. But the method is new, using deep convolutional neural network. I will show you various phase diagrams of Anderson metal insulator transition determined by the neural network in 3D, 2D, as well as 4 dimensions. And then I will show you the phase diagram of quantum percolation transition. And if I have time, I will show you the application of another type of 3-dimensional disordered system, which is topological insulators or Wisen metal. And I will especially emphasize the difference between real space wave function analysis as well as Fourier space, K-space analysis. So what I did is quite simple. In the last decade, there was a very big development of image recognition technique by convolutional neural network. I will use the term CNN for convolutional neural network. If you put a photo, then the neural network judges that this is a cat. Okay. So I decided to use this technique for analyzing the wave function of disordered system. This is, so instead of a photo of a cat, I put a 3-dimensional wave function and then change the neural network so that it outputs metal or insulator, or sometimes in other cases, topological or non-topological. That's what I did. And the main point of this convolutional neural network is that we don't judge the wave function directly from the input, but we change or transform the original input to other images. Then from this image, we transform the image to other type of image, and then go on and go on. And then at the final stage, we judge whether this was a metal or insulator. And since the distance between the input and output are far, we call it deep learning. These are called hidden layers, which typically consist of 2 types of operation. One is called convolution. Convolution is that we pick up a cell inside a system, let's say m by m by m, and then multiply the weight parameter w, and sum the value all over inside the cell, and then we get a new value here. We slide this cell 1 by 1 so that we end up with a new figure or image, 3-dimensional image, which is different from the original one. We prepare another set of weight parameter W, in this case 1, 2, 3, 4, 5. So 5 set of weight parameter W, so that we end up with 5 images which are different from the original one. Then we pick up another small cell and take only the maximum value inside this cell, in this case 2 by 2 by 2 cell. Yes? Yes, right, yeah. Yes, the weight is the same. So, mm. Yes, right, yeah. The same what? Ah, yeah, the 5Q, because W is different. Yeah, yeah, the position is the same. Yeah, yeah. But there aren't any neural network connection between the between the images. Only in this direction we have a connection of the neural network. Okay, and so this operation is called convolution, and this is called pooling. This is largely used to get rid of the noise or fluctuation. So how do we train the neural network? Training, I mean, we need to optimize this weight parameter W so that the neural network correctly reproduces the phase of the wave function. And for this purpose, I use supervised training. This is done as follows. We prepare thousands of wave functions in known phases and teach convolutional neural networks, CNN, that this is metal, this is insulator. During the course of training, I try to minimize the cross entropy, which is defined as follows, where P is the probability or confidence that the I sample with phase J is judged to be phase J with probability P. And P prime is the actual level. By minimizing the cross entropy, we can train the neural network so that it correctly outputs the original, reproduce the original input. Yes. P is the output of the P is the output of the probability that when you input the I sample, you will get Pij, where J is the label. So, but P prime is the actual label. So it is either 0 or 1. I sample is either metal or insulator. We know in advance. Yeah, P prime is the training. So original label. So that, let's do it as an example. If I use P instead of P prime, and if the neural network is stupid and gives all P to be 0, then the entropy is minimum. 0 times log 0 is 0. Or if the neural network gives randomly 0 or 1, 0 for insulator and 1 for metal, then it also gives the 0 entropy. But now, if I use P prime, and for example, I sample is metal, which means 1, let's say, which means 1, so that P prime I 0 is 0, P prime I1 is 1. This is, since it is a supervised training, we know the results. So if I input this value, then the cross entropy will be 0 times log Pi0 minus 1 times log Pi1. So this, so that if Pi1 is 1, the entropy is minimized. So the neural network, by minimizing this cross entropy, the neural network tries to reproduce the correct result. Okay, I pushed something wrong. Okay, in practice, I use only the 90% of the data and 10% is reserved for a test. And once this test is satisfactory, say 98% of the result is correct, neural network output is 98% or more than 98% correct, then we are satisfied with the neural network and prepare eigenfunctions of unknown phases, and let CNN determine the phase. Okay. So let's apply it to the Anderson model of localization. This is energy, site energy, which varies from half W to minus half W. Vj prime j is nearest neighbor transfer, which is 1 for Anderson model. And later, I will change this Vj prime j to U1 matrix to break the time reversal symmetry, or SU2 matrix, so that it includes a spin orbit scattering. And this is the example of the wave function in 2D metal and 2D insulator. Even for us, it's quite easy to guess that this is metal and this is insulator. In the case of 3D, it's more subtle. This is a typical metal wave function, and this is a typical insulator wave function, which is a little bit more difficult than doing it in 2D. And this is what neural network determines, perhaps better than me. So to train the neural network, I prepare 1,000. I have to know in advance whether this is metal or insulator. And for this purpose, I use the information of the result by transfer matrix combined with finite size scaling. And Keith and I estimated it to be 16.54. So I use this information for the training. This value is for energy equals 0, which means at the band center. So if I choose the strength of the disorder between 14 and 16, since it is smaller than WC, it's a metal. So I set this, change the parameter W in this range and produce 4,000 of wave function and label it as metal. I prepared another 4,000 wave function for W between 17 and 19 and label it as insulator, and train the neural network whose structure is as follows, and then diagonalize the Hamiltonian again, and this is the result. So the green region, the region I used for the training. And once the training is satisfactory, I prepared many wave functions outside the band center and let the neural network determine whether it's metal or insulator. And by doing so, we obtain this phase diagram, which nicely reproduces the known result of the Anderson transition. For example, here at the band center, it's insulator. If we increase W, this axis is the strength of disorder W, and this is the Fermi energy. If I increase W, doesn't work, then the system becomes metal, and it becomes insulator again, which is known as the reentrant behavior of the Anderson transition. And the neural network nicely detected this feature of the phase diagram, although it is trained only at the band center. Okay, so at this stage, let me compare the neural network with IPR, inverse participation number. If I plot inverse participation number, average of inverse participation number, we'll get something like this, and we don't know the phase boundary. We can't say anything about the phase boundary from this gradual change of IPR. Another thing is that if I take a log of IPR, it becomes more gradual, and we can't say where the Anderson transition occurred. Now, but we use supervised training. So we can also use the knowledge that of the critical point. For example, we know that this is the critical point. So we can calculate the IPR. We can calculate diagonalize the system at this point and calculate IPR for thousands of systems and can define the critical IPR for this size of the system. Then we can, if IPR is greater than 1, it will be insulator. If IPR is greater than IPR critical, then it will be insulator, and if it is smaller, then it will be metal. So so I plot this step function in this as in the phase diagram of CNN and obtain something like that, which is better than these two, but still the CNN, the convolutional neural network, gives more sharp phase boundary. So there is some advantage of using the neural network over IPR. The reason is that CNN, this is the input of the single wave function, and the CNN gives very sharp, almost constant up to the critical point, and then sharply changes at after the critical point. Now, in the case of IPR, the individual wave functions are very strongly fluctuating. So that is the reason why the phase boundary is less clear if I plot the IPR like this. Now, having said that, I will apply this method to quantum percolation. Already in the morning, we have discussed the percolation, but classical percolation. But what I'm going to do is to apply this CNN to quantum percolation problem. So, case of percolation, bonds are connected with probability P, or sites are connected, sites are occupied with probability P. And in the case of quantum percolation, the Hamiltonian looks like this, where V, J prime J are nearest neighbor coupling, which takes 0 or 1 with probability 1 minus P or P. In the case of site percolation, sites are occupied with probability P, and only when the nearest neighbor sites are both occupied, then the bonds are connected with, I mean the bonds are said to be 1. We know that for D greater than 1, there is a percolation threshold PC. What we are going to do is to create a percolation lattice like this, pick up the largest cluster, diagonalize the Hamiltonian on this cluster. The Hamiltonian is simply this, and obtain the eigenfunction, and let CNN determine the phase. Note that we can't use the transfer matrix method for percolation lattice. So I don't use the transfer matrix, but I use the neural network trained for the Anderson model, hoping that the wave function features are the same. And now let me comment on the quantum percolation threshold. In the classical case, when P is smaller than the percolation threshold PC, all the clusters are finite and the system is an insulator. for P greater than PC, a cluster connecting one surface to the other appears, and the system becomes metal. So the metal insulator transition and the percolation transition occurs at the same time. In the case of quantum percolation, the situation is a bit more complicated. This is the case where P is smaller than PC. All the clusters are disconnected or isolated, and the wave functions are localized on the cluster. So it's both of the cases it's an insulator, both classical and quantum. When P is greater than PC, but smaller than the quantum percolation threshold PQ, we have a cluster connecting from one side of the system to the other, but the state on the largest clusters are localized. Then only when P is greater than PQ, the quantum system begins to carry current. So this is the case of the quantum percolation, and I diagonalize the three-dimensional percolation cluster state on the percolation cluster and obtain the following phase diagram, where PS is the site percolation probability, E is the Fermi energy, and this green dotted line is the classical percolation threshold for site percolation. And green region is the insulator, and red regions are metal. You see is that quantum percolation threshold, which is something like this, depends on the energy, and it is well above the classical percolation threshold. And the dashed line is by Emil Berger and his student, former student, which nicely agrees with the results. Yes? This one or this one? Yeah, we have a strange symmetry at energy equals 0. It has a bipartite symmetry, the percolation cluster. And we have a lot of zero energy states. And another spiky peaks around here is what is called molecular state. Even for the largest cluster, there are some something like dangling bonds, where the states have a specific energy and localized. And that is why the neural network is not so confident that it is metal. Okay, we can use the neural network trained for the original box distribution Anderson model to Gaussian distribution or Cauchy distribution. Well, we can break the time reversal symmetry by modifying the transfer energy to include random pious phases. And the result is as follows. This is what I showed you. This is the phase diagram of Anderson model with Gaussian potential. Again, we observe the reentrant behavior around here to here. This is the Anderson model, but Cauchy distribution of the random potential. And this is the case of Anderson model with U1 phase hopping. Now, the state which was originally localized, corresponding to this region, is now extended, which means that the neural network detected the magnetic field-induced delocalization. This is the case of percolation that I showed you in the previous slide, and this is the quantum percolation, but with magnetic field. And as in the case of U1 symmetry Anderson model, we have the metal region begins to be enlarged towards the localized localized region shrink. Yes.
So these are all results where you determine the phase from the CNN
Yeah.
trained to the normal three-dimensional endoscope.
Yeah, trained only along this region. And the rest of the phase diagram can be drawn. Okay, I have concentrated on the three-dimensional case, but we can do the similar calculation for two-dimensional Anderson transition, which occurs in the case of symplectic cluster, strong spin-orbit scattering. Here we chose the nearest neighbor transfer as this 2 by 2 SU2 matrix. 2 by 2 means we include the spin degree of freedom. And then the result of the phase diagram is as follows. You see, even for W equals 0, so even if there aren't any site disorder, because of the random spin-orbit scattering, the system is disordered, and we have a small but finite region of localized state around here at the band edge of the system. And this dashed line is what Dr. Asada and Keith and myself estimated a long time ago, which nicely coincides with the neural network result. This is for the two-dimensional quantum percolation. Again, the quantum percolation occurs well above the classical percolation threshold. Maybe you are bored, but this is for the four-dimensional four-dimensional Anderson transition. Well, the system size is smaller because of the limited memory. So the phase boundary is less clear, but we see that these are the localized state and these are the extended state, and this is the case of quantum percolation in 4 dimensions, which is drawn by the neural network trained along this small region of phase space. Again, the quantum percolation occurs above the classical percolation threshold, but the distance between the classical and the quantum percolation thresholds are beginning to be smaller and smaller with the dimension. At least that's what neural network tells me. Yes? Yeah, I have to train again. I tried to integrate one direction, and for example, I integrate the wave function along one direction, making it a two-dimensional image, and use the two-dimensional neural network to detect the phase transition. It worked not so bad, but training the neural network for the 3D instead of integrating it over one direction is even better. So I can integrate the 4D wave function along one direction to have a 3D wave function, but doing it directly in 4D gives a better result. So I still have 10 minutes or so, so that I will talk about real space wave function and the advantage or disadvantage of using the real space wave function. So far, I have been using the real space wave function. The question is, would it be better if we train the neural network using wave functions in K-space? K-space means just Fourier transform the wave function, or Fourier transform the wave function in Y and Z direction, while X direction is just remain to be the real space coordinate. And I apply this idea of using the k-space wave function to analyze the topological insulator. Before going into detail, I will just go over the real space, show you the real space wave functions. This is a typical method. UTI means weak topological insulator with index 111. The index ijk means that surface states don't appear on surfaces normal to ijk. So in this case, if we cut the system normal to 111 direction, we don't have any surface state. This is the case of weak topological insulator 001, which is this direction. STI is a strong topological insulator. Wire-same metal 2 and wire-same metal 3 means we have 2 pairs of wire nodes, 3 pairs of wire nodes. So we can say that there are surface states, but it is difficult to distinguish STI from WTI or WTI 111 from WTI 001. The same is true to, it's difficult if we work in the real space wave function to distinguish wire-same metal 2 from wire-same metal 3. But in the case of k-space, the situation changes. In the case of where we should distinguish metal from insulator, it is worse. It's better to work in the real space. But in the case of topological insulator, now even in the presence of randomness, we see a sharp structure which is located at 0 pi or pi 0 or 0, 0. So if we switch to the k-space, the wave function feature is more clear. So I will go into the detail of the topological insulator, beginning with the what is called minimum model for 3-dimensional insulator. But this is the Hamiltonian with W equals 0. Alpha and beta are gamma matrices 4 by 4. Sigma is the Pauli matrices. And M naught controls the gap of the band. And if M naught is greater than 0, it's an ordinary insulator. While if M naught is something between 0 and -2, the surface Dirac cone, a surface Dirac cone appears in the middle of the band. And now and this corresponds to the surface state. Now if M naught, this guy is between -2 and -4, we have 2 Dirac cones. And there are scattering between the 2 Dirac cones, and that's why we call it weak. So this is, again, the wave function for weak topological insulator and strong topological insulator. And when we go to the Fourier transformed wave function, then although they look the same, the Fourier transformed wave functions are very different. Yes? Because I have an impurity. So the symmetry between the upper surface and top and bottom are broken. And I'm choosing the state which is closest to energy equals 0. So if we change the randomness, then we happen to have a surface state at the bottom. Thank you. Okay, this is the result of, this is the phase diagram of this 3-dimensional topological insulator, where the neural network is trained for real space. You see this is the band gap parameter and the strength of disorder. the arrows are where I train the neural network. OI is the ordinary insulator, which becomes strong topological insulator, weak topological insulator, and weak topological insulator 1, 1, 1. You know the phase boundary is not clear in this case. While if I train the neural network in K-space, the same wave function, but fully transformed, the phase boundary is much more clear, and you see that as we change W, the phase boundary changes. And if I start from here and increase this order, the ordinary insulator becomes strong topological insulator, which is known as the topological Anderson insulator. And the neural network actually captures this behavior. We also note that we have a green line on the phase boundary between OI and STI. And in fact, there appears a Dirac semi-metal on the phase boundary, which is captured by the neural network. But I have to comment that the phase boundary between the metal and the topological insulator is not consistent with the transfer matrix, the solid lines estimate by the transfer matrix method. And you see that the phase boundary deviates from the neural network phase boundary to the metal phase, deviates from the transfer matrix method. For if we work in the real space, the phase boundary between metal and topological insulators are better, which means that depending on the nature of the phase transition, sometimes K-space analysis is better, and sometimes real space analysis is better. I still have time? Yeah. Okay, 7 minutes. So then in the last 7 minutes, I will explain the wire semi-metal. Now, in the last 5 or 3 years, many 3D wire semi-metal have been discovered, which is characterized by Y node, P node, and the Hamiltonian near the P Y node plus minus P node is effectively written as vector P dot Pauli matrix sigma, and the energy dispersion becomes linear in P plus minus P node. Plus minus P node is the location of the Y node that appear in pairs, and what I'm going to do is to draw the phase diagram in the presence of randomness. The model I use is a Chern insulator model, but three-dimensional Chern insulator model, where a site consists of S orbital and P plus orbital. P plus is equal to Px plus IPy. And they are arranged in on a square lattice in 2 dimensions, then piled up in the 3rd dimension. So the Hamiltonian is a bit complicated in this case. ES is the energy of the S orbital. EP is the P orbital energy. VS and BP are random potential. TS and TP, these terms are transferred between the nearest neighbor, between S orbital and between P orbital, and this is mixing of the S and P orbital during the hopping from one side to the other. And the last term is the 3rd direction, the hopping in the Z direction. So we will see what happens if we increase the interlayer coupling, which is characterized by Yes? In the limit of 2D, the system is as follows, where we have Chern insulator and the whole conductivity is quantized to 1 if EP, the energy of p orbital and the energy of s orbital difference is small enough. If they are big enough, then it becomes an ordinary insulator. Now we pile it up to have something like this. Without disorder, the Hamiltonian looks like as follows: A dot sigma, where A 1, 2, 3 sine ky, sine kx, and this form. So that in order for the gap to close, sine kx and sine ky, all of them, A1, A2, and A3 should be 0. So that sine kx, sine ky are either 0 or pi. And this guy, A3, should be 0 by choosing this value of cosine kz. And in fact, this is the band structure of this K, of this system, where we observe the band touching, linear band touching, which appears in pairs here, here, and here. So this is the Y-same metal without disorder. And the actual phase diagram without disorder is as follows, where in the absence of interlayer coupling beta, the system is either Chern insulator or ordinary insulator. Alpha is the distance or energy difference between s and p orbitals. While if we increase the interlayer coupling beta, then the both ordinary insulator and Chern insulator becomes Y-same metal. Y-same metal region 1, region 3, and region 4 or region 2 means there are 2 pairs, 1 pair, 3 pairs, 4 pairs, and 2 pairs of wild nodes. Now, what happens if I'm running out of time? So, So, what happens when we when we introduce disorder? So, we know that at 0, in the limit of 2 dimensions, beta equals 0, the system becomes Chern insulator to Anderson insulator at WC. If we increase the interlayer coupling, the critical region is broadened and there appears a finite range of metal state. Now, if we set W equals 0 and increase the interlayer coupling beta, then the Chern insulator becomes Y-same metal. The question is what happens around here. And this can be captured by neural network. And the result is as follows. As is the case in the Anderson transition, I train the neural network in a certain region of phase diagram and draw this phase diagram where the Chern insulator, Y-same metal, and diffusive metal phase boundary changes as we change the strength of disorder. But if we look at the phase diagram in detail, the self-consistent Born calculation indicates that this Y-same metal phase consists of Y-same metal 2 and Y-same metal 3. This is the phase diagram expected from the self-consistent Born approximation. This is the global phase diagram drawn by the transfer matrix method, and the result coincides, but the neural network trained for real space cannot distinguish Y-same metal 2 and Y-same metal 3. While if we work in the K-space, the K-space wave function for the wires and metal 2 and 3 are totally a little bit different, so that the neural network can distinguish wires and metal 2 and 3. So I need to summarize. What I have shown you is that neural network can draw the phase diagram of quantum phase transition of random system, Anderson and quantum percolation, 3D, 2D, and 4D, as well as topological insulator and wires and metal. Thank you for your attention. Yes. Yeah.